Well, welcome. Today's lesson on molecular and structural formulas of organic compounds are brought to you by the letter C and by the letter H. Together they form a hydrocarbon. So, without further ado, let's get right into it. So you have this worksheet. I'm going to hit a couple of the highlights, and then we're going to turn you loose and see if you can figure this out. So the very first one is pentane, and we will do this one together. So when we start with the molecular formula, we have to first figure out what the root of the name is and the suffix. Well, the root is pent. That means there are 5 carbons. So we're going to write C5. The ane means we have an alkane. And because it's an alkane, the general formula for an alkane is CnH2n plus 2. Therefore, being 5 carbons, the number of hydrogens is going to be twice the number of carbons plus 2, making it C5H12. So now we have to draw the structural formula. First, we know that we have 5 carbons, so we're going to draw 5 carbons all in a row, all connected with a single bond. We're going to start with a single bond. Because this is an alkane, ane, they all are going to stay connected as a single bond. We now know that we have 12 hydrogens to assign. Each carbon can only accommodate 4 single bonds. So therefore, we have to understand that the terminal, the end carbons, those two can only accommodate 3 more bonds. The interior carbons, those all are already making 2 bonds with the carbons next to them. So these 3 can only accommodate 2 more bonds. When we get done, we can draw all the hydrogens in. Remember, we don't need to draw the actual H's. We can just draw the lines without the H's attached, and you're going to have that. And so that is the structural formula for pentane, and that is the molecular formula for pentane, C5H12. If we jump ahead to hept3-ine, that is the first one that involves a number. So let's figure this out. So we start with the root, hept, which means 7. So we have C7. And then we look at the suffix of ine, and that indicates that it is an alkyne. So the general formula for the number of hydrogens is twice the number of carbons minus 2. So if we take 7 times 2, 14 minus 2, we're going to get a grand total of 12 hydrogens, C7H12. We're not dealing with the 3 yet because the 3 is telling us where something is. And the thing it's telling us is where that triple bond is. So first we're going to draw out 7 carbons, all singly bonded. So now we have our 7 carbons. We now need to identify what the 3 is. Well, the 3 tells us that's where the triple bond has occurred. So the triple bond is going to occur on the 3rd carbon. If we count from the left, the 3rd carbon will be this one. But if we count from the right, the 3rd carbon will be this one. It really makes no difference which one you choose because it is symmetrical and you're counting either from the left or the right, and this thing is in the 3 dimensions, and which end is the beginning and which is the end, it really doesn't matter. So I, being just a little type A, I like having my things start from the left to the right, but if you want to go from the right to the left, that's fine. So I'm going to choose this one as the 3rd carbon. So now it indicates that we're going to have our triple bond there. Now the triple bond is not because of the 3, the triple bond is because of the ine. We have a triple bond in this because it's an alkyne, so we're going to put our triple bond right there. And so now that 3rd carbon has a triple bond. It's triply bonded to the 4th carbon as well, but it initiates at the 3rd carbon, so that's why it's the hept3-ine. The 3rd carbon is the one that identifies it. Now we need to assign the number of hydrogens. Well, we have 12 hydrogens to assign. We need to understand that each carbon can only have 4 bonds. These 2 are already making 4 bonds, 3 bonds to each other, then 1 bond to the other side. The other carbons in the middle are only making 2 bonds, so they can each make 2 more bonds to hydrogens. And that leaves our terminal or the end carbons, and they are each making 1 bond currently, so they can each accommodate 3 more. So if we consider this, we now have our 12 hydrogens. We have our triple bond on the 3rd carbon, and that is hept3-ine. Let's jump ahead to something different. Well, these are different. 2-methylhexane, 2,3-dimethylpentane, 2,2,3-trimethylbutane. They all contain substituent groups. And a substituent group is a carbon group that is attached to the main hydrocarbon chain. In this case, we have methyl groups. Now, the first one has 1 methyl group. The second one says dimethyl, which means that it has 2 methyl groups. The third one has 3 methyl groups, which means it says 3 methyl groups. So the words tell you what it is, and the numbers tell you where. So in the first one, 2-methylhexane, we're going to have 1 methyl group, and it's going to be on the 2nd carbon of a hexane chain. So if we consider the hexane chain to be 6 carbons in a row, and we want to count from the left, that 2nd carbon there is our 2nd carbon that's going to have the methyl group on it. A methyl group is a carbon group that only has 1 carbon because it contains a meth. So it's going to have a 1 carbon substituent group hanging off of that 2nd carbon. So there's the carbon hanging off the 2nd carbon. And now we're going to go through and fill all the other carbons with the total number of hydrogens that they can hold. Remember, we have an alkane because it's a hexane. Therefore, all of them are going to be having single bonds between the carbons, and all of them can have a maximum of 4 bonds. The first carbon only is making 1 bond, so it can make 3 hydrogens attached to it. The 2nd carbon that the methyl group is attached to, it's currently making 3 bonds. So those 3 bonds are connecting that 2nd carbon to the methyl group and to the preceding and following carbon. So it can only accommodate 1 hydrogen. The methyl group, it's a carbon. It's only making 1 bond so far. So it can accommodate 3 more hydrogens. And so now we're moving into internal carbons, center carbons. They each are making 2 bonds, so they can accommodate 2 hydrogens each. And then that brings up our terminal carbon, our last carbon, and that one also can take 3. So 1, 2, 3. And so we are done. We have 2-methylhexane. Our methyl group is on the 2nd carbon. We have only 1 methyl group, and it's there on the 2nd carbon. The hexane is the long chain, so that's the 6 carbons in a row. And so there we go. The next ones involving substituent groups have multiple substituent groups. That means we're going to have a methyl group. And remember, the methyl group is just this, a carbon that has 3 hydrogens on it. If it were an ethyl group, it would be 2 carbons with the requisite number of hydrogens. So now the last step is here to draw our molecular formula. And this is a little bit tricky sometimes. It's easiest if you break it up into its different components. And when you do that, it's going to look like this. CH3, CH with a CH3 attached to it, and then 4 carbons, C4, with 9 hydrogens attached to them. I hope that helps a little bit. So now the rest of this is just putting this formula into the molecular formula. This is called a structural molecular formula. And we just move it there. So there's our CH3CH, CH3C4H9. We can simplify this and end up with C7H16 as the general molecular formula. But the structural molecular formula will be CH3CH, CH3, C4H9. All right, Give it a try.